Hello dear students, welcome to Mohammed Fugazi YouTube channel. Today we are discussing about Gauss Divergence Theorem. Well, you already know the concept of divergence, as we know that divergence of any vector field gives the net outward flux of a vector field per unit volume. Now jump on to the statement of Gauss Divergence Theorem. Statement: if V is a volume bounded by a closed surface S and A is a vector function of a position with continuous derivatives, then the volume integral of the divergence of vector A is equal to the surface integral of the net outward flux of vector A, where n is the positive outward drawn normal to S, that is, the surface integral over a closed surface S of any vector A is equal to the volume integral of the divergence of A over the volume enclosed by S. This theorem relates the total flux of the vector field out of the closed surface to the integral of the divergence of the vector field over the enclosed volume V. Let's jump to Let's jump onto the statement again. What this theorem tells us: the right-hand side of the mathematical expression of Gauss divergence theorem is the total flux of a vector field of a closed surface S, which is related to the integral of the divergence of the vector field over a closed volume V. Let us make our discussion purposeful that why we used to study the Gauss divergence theorem. I'll give you two examples so that you will be able to understand the significance of Gauss divergence theorem. You guys have to listen very carefully because these examples are hypothetical and I don't have any slides to show for their illustration. Well, as a first example, suppose you go to the gas station and pump air into one of your car's tires. I ask you guys, what has to happen to the tire? What has to happen to the air inside the tire? Before thinking of the answer to this question, let us assume that the tire is rigid and does not expand as you put air inside it. Well, the answer is straightforward. You don't need to overthink about it. Obviously, the air inside the tire compresses. Now, we describe this process in terms of mathematics. Suppose this A represents the flow of air. Then in this case, the divergence of A gives the compression of the air inside the tire. The divergence theorem says that this compression of air inside the tire having inner volume V is equal to the net influx of the air into the boundary of the tire of the car. As a second example, suppose you have a rigid container filled with some gas. If the gas starts to expand but the container does not expand, what has to happen? We assume that the container does not expand, it is rigid, but the gas is expanding. Then the gas has to somehow leak out of the container. This example also illustrates the divergence theorem. Suppose in this case this A represents the flow of gas inside the container, then the divergence of A represents the expansion of gas in the container. The divergence theorem in this case says that the total expansion of the gas inside the container having volume V equals to the total flux of the gas out of the boundary of V. The boundary is of course the surface S. So you have noticed in these examples the vector field A represents the flow of the fluid and its divergence gives the expansion or the compression of the fluid. So due to its importance, it is vastly used in fluid dynamics and many other fields of mathematics. Well, there are certain conditions for a vector field A. What are the conditions that are imposed on the vector field? That is, what are the conditions that are implemented that we can implement on A so that this theorem is valid for a vector field A? Can every vector field satisfy this theorem? The answer is no. So what are the necessary conditions for the vector field to satisfy Gauss divergence theorem? If a vector A and its derivatives are continuous in a region, then the Gauss theorem can be applicable. We talk about the misconception, a common misconception uh, which we are studying when we are studying about this theorem. The students develop some misconception about this theorem. Gauss divergence theorem is not the conversion of surface integral into the volume integral and vice versa, because we know that there are four types of surface integrals, in which one includes the cross product, second in which phi is a scalar function, third in which phi is a scalar function where the differential is a vector, and the fourth one is the dot product of two vectors. It means you cannot convert the surface integral into the volume integral by using this theorem. This theorem is applicable for the last surface integral only. That is, this integral can be written as a volume integral instead of the above three. So saying that it is a conversion of surface integral into volume integral is not true. Because if we say that a surface integral can be converted into volume integral, then it means that all of these forms of surface integral can be converted into volume integral, which is not the case. Only the last one can be expressed as volume integral. So you guys have to take care of it. Now let's jump onto the proof of Gauss divergence theorem. Let us consider a closed surface S which is such that any line parallel to the coordinate axis cuts S in at most 2 points. Now we are considering the surface S, which is in the form of sphere here, such that we draw any line parallel to the coordinate axis through S. Here we have drawn a line parallel to the z-axis. Then it will intersect at most at 2 points. Usually we consider this surface as sphere or ellipsoid, etc. Here the word "at most" is used, which emphasizes that the line drawn can either passes parallel to the coordinate axis without touching. That is, if I draw a line here parallel to the z-axis, then it will pass without touching the z-axis, without touching the surface S, or either it touches the surface S at a single point, that is, it is tangent to the surface, that is, if I can draw a line parallel to the z-axis, then it will touch here and here. That is, the line drawn is tangent to the surface. Another possibility that the line that we describe here is the line passes through the surface and touches it at 2 points. These are the points, this and this. We further suppose that R is the orthogonal projection of the surface. R is the orthogonal projection of the surface on the xy plane. Assume the equations of the lower and the upper portions S1 and S2 to be z is equal to f1 of xy and z is equal to f2 of xy respectively, as shown in the figure. Let the projection of the surface on the xy plane be denoted by R. What we have done that we split the surface into two portions, the upper portion and the lower portion. The upper portion is named as S1 and the lower portion is named as the upper portion is named as S2 and the lower portion is named as S1. Now, what does the first line mean? If we draw a line parallel to z-axis from a point located in the xy plane, this is a point in the xy plane, then this line meets the surface S at 2 points. We divide the surface into two parts, S1 and S2, containing 2 points whose z components are z1 and z2 respectively, where this z2 is greater than z1. The x and y components of these points of intersection of the line with the surface remains the same. Here you can see that nothing, uh, no change in the x and y coordinates. Here the x and y coordinates remains the same and x and y coordinates remains the same. The only variation is along the z-axis. You see that the point in the xy plane has z coordinate 0 and the point here has z coordinate z1 and the point here has a z coordinate z2. If we assume this surface to be sphere, if this surface is sphere, then we know that the equation of sphere is x square plus y square plus z square is equal to a square, which gives z is equal to plus minus under root a square minus x square minus y square. For upper portion, the equation is z is equal to plus under root a square minus x square minus y square, and for the lower portion, the equation is minus under root a square minus x square minus y square. Thus, the S1 and S2 are functions of x and y. Thus, depending on the shape of the sphere, the upper and lower portions of the surface S have equations z is equal to f1 of xy and z is equal to f2 of xy. The equations of the surfaces are the functions of two variables x and y. Now let's get back to the where we have ended. If A is equal to A1i plus A2j plus A3k, where this A1, A2 and A3 are functions of x, y and z and their derivatives at any point in the volume V are continuous. Now, in order to prove the theorem, we start from the left-hand side of the mathematical expression of the Gauss Divergence Theorem. Let's see what the Gauss Divergence Theorem says. On the left-hand side, we have the divergence of the vector function A, but we have already let it that the vector function A will let it a1I plus a2j plus a3k. Hence the divergence of vector function A is partial a1 by partial x plus partial a2 by partial y plus partial a3 by partial z. And to compute the volume integral of this divergence, we have to separately compute the volume integral of partial a1 by partial x, partial a2 by partial y, and partial a3 by partial z. And by adding these three volume integrals, we get the left hand side of our theorem. So for this we consider the triple integral, the volume integral partial a3 by partial z, and try to compute it, and after computing it we see if we see any symmetry, then we will write the expression for the volume integral of partial a2 by partial y and partial a1 by partial x, and their results are simply added and we prove the theorem. Now what this statement says that the volume integral of partial a3 by partial z is equal to the volume integral of partial a3 by partial z, and instead of writing dx, dy and dz can be written, which is equal to the double integral over r and partial a3 by partial z. The integral is the single integral of the partial a3 by partial z integrated over z dy dx. Here we integrated partial a3 by partial z with respect to z, and note that the z coordinate varies from z is equal to f1 of xy to z is equal to f2 of xy. Here you can see that the z coordinate varies from z is equal to f1 of xy to z2 is equal to f2 of xy. This result is integrated with respect to x and y. Here we have written r because we already see that x and y coordinates did not change when we draw a line parallel to z-axis through the surface S from a region R. So instead of writing S1 or S2, we can integrate the result obtaining from the innermost integral over a region R. The innermost integral results a3 with limits z is equal to f1 to f2, because the differentiation and integration cancel each other, and when we put the limits, what will happen? The volume integral of this partial a3 by partial z results into a3, which was a function of x, y and z, and after putting the upper limit we get f2, and a3 which was a function of x, y and z, and after putting the lower limit we get f1 here. Here it has been cleared earlier that this a1, a2, a3, which are the components of this vector function A, these components are the functions of x, y and z. So you guys have to take care about it. Now here we suppose that this n2 be the unit outward drawn normal vector making an angle gamma 2 with k. Here you see that gamma 2 is an acute angle. Since the unit normal n2 to s2 makes an angle gamma 2 with k for the upper portion s2, If ds2 is projected on xy plane, this ds2 is projected on xy plane, then its projection is dy dx or dx dy. Now we uh, now this dy dx can be calculated as dy dx is equal to projection of ds2 in xy plane, which is equal to cos of gamma 2 ds2, which is equal to the dot product of k and n2 into ds2. Now how can you find this cos of gamma 2? Consider this dot product k dot n2, and you can verify by the definition of dot product that k dot n2 is equal to cos of gamma 2. The projection of ds2 in the line integral, you know that how can we find the projection of a surface ds2? It is equal to the cos of the angle and ds2. And how can you find the cos of gamma 2? Cos of gamma 2 can be found by using this dot product k dot n2. The definition of dot product gives you cos of gamma 2, since the angle between k and n2 is gamma 2. So the definition of dot product gives you cos of gamma 2. Using this for upper portion, we have double integral over r of a3 xy f2 dy dx is equal to the surface integral a3 k dot n2 ds2. Similarly, we suppose that n1 be the unit outward drawn normal vector making an angle gamma 1 with k. Here you can see that gamma 1 is an obtuse angle. Here in the previous we have used f2 instead of r because the differential here is ts2. Similarly, since the unit normal n1 to s1 makes an obtuse angle gamma 1 with k for the upper portion s1, if ds1 is projected on xy plane, then its projection is again dy dx or dx dy. Now this dy dx is given by dy dx is equal to projection of ds1 in xy plane, which is equal to cos of pi minus gamma 1 ds1, and cos of pi minus gamma 1 can be written as minus cos of gamma 1, and this cos of gamma 1 is again can be calculated by the dot product of k and n1. You can easily verify by the definition of the dot product that k dot n1 is equal to cos of gamma 1 because the angle between n1 and k is gamma 1. Using this for lower portion, we have the double integral over r of a3 xy f1 dy dx is equal to the negative times the surface integral over s1 a3 k dot n1 ds1. Here we use s1 instead of r because the differential is ds1. Subtracting 4 from 3, we have the double integral over r of a3 xy f2 dy dx minus double integral over r of a3 xy f1 dy dx is equal to the surface integral over s2 of a3 k dot n2 ds2 plus the surface integral of s1 of a3 k dot n1 ds1. You see from this can be easily written from 4 and 3, which implies the surface integral of a3 xy f2 minus a3 xy f1 dy dx. We combine the left hand side, which results here, and the right hand side gives the surface integral a3 k dot n df. Now the sum of these two integrals on the right hand side can be replaced by a single surface integral taken over a whole surface S, and instead of writing the normals n1 or n2, we write here the normal n, which is drawn outward from the surface S. Putting this last result in equation number 2, we get the volume integral of a3 partial a3 by partial z dv is equal to the surface integral of a3 k dot n ds. This is the surface integral of partial a3 by partial z. This is the volume integral of partial a3 by partial z. Similarly, we can find the volume integral of partial a2 by partial y and the volume integral of partial a1 by partial x, and on adding them we get the left hand side of our statement. Similarly, the volume integral of partial a2 by partial y dv is equal to the surface integral a2 j dot n ds, and the volume integral of partial a1 by partial x dv is equal to the surface integral of a1 I dot n ds. So adding 7, 6 and 5, we have the volume integral of partial a1 by partial x dv plus the volume integral of partial a2 by partial y dv plus the volume integral of partial a3 by partial z dv is equal to the sum of these surface integrals on the right hand sides of 5, 6 and 7. This can be written as the left hand side can be written as partial a1 by partial x, this volume integral of partial a1 by partial x plus the plus partial a2 by partial y plus partial a3 by partial z, and the right hand side gives us the surface integral of a1i plus a2j plus a3k dot nds. Now, what is this term? This term is the divergence of the vector field A. This implies the divergence of the vector field A is equal to the surface integral, and this is the vector A, which is equal to the surface integral of the outward flux of the vector field A. This completes the proof of our theorem. Now we discuss an important result which we can uh, which we can draw from the physical significance of divergence. As you guys know that the divergence gives the net outward flux of a vector field. In case of fluids, it gives the net outward flux of the fluid. Now, the divergence of a vector field, as we already know, it gives the net outward flux of of that vector field per unit volume. The divergence of a vector field A is defined by del dot A is equal to the net outward flux per unit volume. This is the net outward flux from a surface delta S per unit volume, and the volume tends to 0, where n is the positive outward drawn normal to delta S. Now let's shift this delta V onto the left hand side. We get del dot A into del V is equal to the net outward flux of this vector field A, where delta V approaches to 0. This implies the summation. We take the summation on both sides, uh, varying from 1 to n. If this n tends to infinity, we have the volume integral del dot A dv. This summation is converted into the volume integral, and this summation is converted into the surface integral when n tends to infinity. And guys, what is this? This is a mathematical expression for the Gauss divergence theorem. Thus, we can say that the Gauss divergence theorem is actually the physical significance of divergence. Hope you get the topic. Thanks for watching this video. Please like, subscribe and share this video.